Good morning. I would like to introduce you the one of the experiment. We use the experiment called the single sheet tester to test the characteristic of the steel. Single sheet tester is like this. We have a yoke. This is the yoke. We have the yoke. Okay. We have a tester sample. Single sheet, and then when I draw it in here, it becomes like this. Okay, then we have the input of the voltage from here, which is the same from here. Then we have two wires. This is not one wires, and this one another one wires. So I have a measure V1, V2. Okay, with two coil, one coil, two coil. Okay, one coil with one V1, another coil with one V2. Okay, this is metal sheet. We have a non-grain metal sheet with a 0.5 mm. We also have one metal sheet which is a grain with a 0.3 mm thickness. This is thickness 0.5 mm, 0.3 mm thickness. Okay, now in this experiment, what we need to do is we need to inject the voltage in the AC form. AC form. It must be AC. Okay, we will inject the voltage to create a flux. Okay, the flux will flow from this is the coil. I create the flux will flow from here, inject to the metal sheet. Okay, then come back to here, come back to here. So when the flux is created, it will go down, go through this yoke. We call this one is a yoke, Y-O-R-K. And then we'll go through, and then through the plate, and then go back to the yoke, go back again. So inside here we can see there's a lot of a strip. But the yoke is actually constructed by a lot of pieces of a steel. So I just draw it like here. It is only 1, 2, 3, 3 metal steel. Okay, we need to know what is the direction of this. What is the good direction for the flux to flow through. So we have an easy and hard direction. In order to test on this, we need to conduct, we call SST, single sheet tester. Okay, so how we want to do that is we need to do some calculation by using V equals to 4.44, BNFA. B, we need to know that what B we want to create here. B means the magnetic flux density. N means the number of turns of the winding N here. And then the F is the frequency that we inject here. A is the area of the yoke, where the flux flowing through perpendicular 90 degree. Okay, perpendicular 90 degree to this one. Okay, so I draw it like this one, and then extract it to become like this. Okay. So and the area will be like this. We need to calculate the area here. So the most simple one, if I say I have an X, I have a Y, I need to use X times Y. But now, okay, for example, I have an X, I have a Y. So what I need to do, I use X times Y. So my X is my width. What about my Y? My Y is I have a piece of this is the thickness. So my Y, for example, in this case, I have 3 pieces with this thickness. So my Y is 3 times T. But what if I don't know how many number of layers? So I use N, which is equal to N times T. So I use N times T, which is the same as N cross T times width. So N is the number of the layer. We have the layer here is about 40. Then the thickness of the steel we are using is 0.3 mm. After that, the width here is about 3 cm. It's given. So we have A, we already have N, we already have a T, we have a W, then we have A. Then we have a F. N is the number of turns of this one, 125 turns. We already have it. And now we need to know what is the voltage. So, for example, if let's say I want to have 0.2 Tesla, what type of the voltage I need to have? So I need to calculate that. I need to use 4.44 times 0.2 times this one times this one times this one, so that I can get V. For example, I have a 3 volt. So which means that when I do the experiment, I need to inject 3 volt. Remember, 3 volt is AC RMS. 3 volt, then I will get 0.2 Tesla. Same as well, if let's say I need 0.3 Tesla here, so I substitute 0.3 Tesla and redo the calculation, I maybe have a 5 volt. So, which means when I do the experiment, I need to inject 5 volt to get the 0.3 Tesla of the fluxes. Okay, now, after we already inject the fluxes, what we need to do is we need to measure the V1 and V2. So, as we know that when there's a fluxes, for example, the fluxes is going to this way, I have a conductor. So, if my fluxes is changing, okay, if my fluxes is changing, I'm using Fleming right-hand rules, okay, I'm using Fleming right-hand rules, E equals to L dot V cross B, okay, my B is changing, AC, my V, do I have V or not? I seems do not have V. Fleming left-hand rules or Fleming right-hand rules? Fleming left-hand rules. Fleming left-hand rules. BLV, BLV. Fleming right-hand rules. So velocity. What about my velocity? Do I have velocity? No, I don't have velocity. So how? I don't have velocity, I have an inductor. L. Fleming left-hand rules, F equals to VIL. But that one is a force. You create a force instead of create of this one. How to explain this one? If my B is AC, okay, we are using the Fleming's right-hand rules because the velocity already occupied by the AC here. So we have the length, so we can generate EMF. We have B, which is in arbitrary motion, pergerakan yang tidak dinampak, which is mimic to V, and then we times with the length of this one or this one, then we can get our EMF. So the major thing is it must be crossed. Okay, when the B is moving, then the inductor must be crossed. Then we will get our EMF. But if the inductor is like this, we have like this. If the inductor is like this, which means the B is not crossing any of the conductor, so we do not have E. E will become 0. For example, in this case, the fluxes is going back, go and back, go and back. So if let's say we place in a good position, the conductor here is actually cut with the flux in this way. Then we will get some value for V1. And then at the same time, we also measure V2. V2 which is in the scene of this one, whereby the fluxes go and back, but there's no cutter on the winding. So expected will be 0. Expected will be 0 or nearly to 0. Then we have some value here. Okay? So we need to conduct the experiment from 0.2 to 1 Tesla with the interval of the 0.1 Tesla. Means I have to 0.2 and then 1 V, 0.3 second V, 0.4 second V. Then I inject, then I measure. After that, I need to switch the position. Okay? I need to switch the position. For example, after I do all the experiments to get the 0.2 and 1.0 Tesla, I switch the position from here to here. And then I inject the voltage to measure the induced voltage. Okay, so anything else? No more. Thank you so much.